Welcome to our deep dive into the fascinating world of organic chemistry. Today we'll be exploring three important classes of compounds: aldehydes, ketones, and carboxylic acids. These molecules play crucial roles in both nature and industry, forming the backbone of many biological processes and everyday products. Before we get into the details, let's set the stage by understanding what makes these compounds unique and why they're so significant in the study of chemistry. Get ready for a journey through structure, properties, and applications. Aldehydes are organic compounds characterized by the presence of a carbonyl group bonded to at least one hydrogen atom. This functional group, written as CHO, is what gives aldehydes their distinct chemical behavior. You'll find aldehydes in nature, such as in the aroma of cinnamon and vanilla, and they're also used in the manufacture of dyes, perfumes, and plastics. Their reactivity makes them essential intermediates in many chemical reactions. Let's look closer at their structure and see what sets them apart from other compounds. Structure of an aldehyde is simple yet distinctive. The carbonyl carbon is double bonded to an oxygen atom and single bonded to a hydrogen atom, with the remaining bond connecting to an alkyl or aryl group. This arrangement makes the carbonyl carbon highly reactive, especially towards nucleophiles. The planar geometry around the carbonyl group also influences how aldehydes interact with other molecules. Understanding this structure is key to predicting their chemical behavior and reactivity. Aldehydes generally have distinctive odors, often pleasant or pungent. They tend to have lower boiling points than corresponding alcohols due to the absence of hydrogen bonding between molecules. However, their boiling points are higher than those of hydrocarbons of similar molecular weight. Most lower aldehydes are soluble in water, thanks to their ability to form hydrogen bonds with water molecules. These physical properties influence how aldehydes are used in industry and everyday life. Aldehydes are known for their reactivity, especially in oxidation and reduction reactions. They can be easily oxidized to carboxylic acids, a transformation that is central to many metabolic pathways. Aldehydes also participate in addition reactions, such as nucleophilic addition due to the electrophilic nature of the carbonyl carbon. These chemical properties make aldehydes versatile intermediates in organic synthesis and industrial processes. Let's look at some common aldehydes you might encounter. Formaldehyde, the simplest aldehyde, is widely used as a disinfectant and preservative. Acetaldehyde is found in ripe fruits and is an intermediate in alcohol metabolism. Benzaldehyde gives almonds their characteristic aroma and is used in flavorings. These examples show the diversity and importance of aldehydes in both nature and industry. Now let's shift our focus to ketones. Like aldehydes, ketones contain a carbonyl group, but with a key difference. The carbonyl carbon is bonded to two other carbon atoms, not to hydrogen. This structural variation leads to different chemical and physical properties. Ketones are found in a variety of natural and synthetic substances, including solvents, fragrances, and even in our own bodies as metabolic byproducts. Defining feature of ketones is the carbonyl group bonded to two alkyl or aryl groups. This is typically represented as RCOR, where R and R are carbon-containing groups. The absence of a hydrogen atom attached to the carbonyl carbon distinguishes ketones from aldehydes. This structure affects their reactivity and the types of reactions they undergo, making ketones important in both biological and industrial contexts. Ketones generally have pleasant, sweet odors and are often used as solvents due to their ability to dissolve both polar and nonpolar substances. Their boiling points are higher than those of ethers but lower than alcohols of similar molecular weight. Many ketones, especially lower ones like acetone, are miscible with water, making them versatile in laboratory and industrial applications. Ketones are less reactive than aldehydes towards oxidation, but they still participate in a variety of chemical reactions. They undergo nucleophilic addition reactions, similar to aldehydes, but are resistant to further oxidation under normal conditions. This stability makes ketones useful in many synthetic pathways, including the production of plastics, pharmaceuticals, and other chemicals. Some well-known ketones include acetone, the simplest and most widely used ketone, found in nail polish remover and as a laboratory solvent. Another example is butanol, used in the production of plastics and textiles. In our bodies, ketones like acetosacetone are produced during fat metabolism, especially during fasting or low-carb diets. These examples highlight the practical importance of ketones in daily life. While both aldehydes and ketones contain the carbonyl group, their structural differences lead to distinct chemical behaviors. Aldehydes are generally more reactive due to the presence of a hydrogen atom attached to the carbonyl carbon, making them more susceptible to oxidation. Ketones with two carbon groups attached are more stable and less reactive. These differences are crucial in determining their roles in chemical reactions and industrial application. Carboxylic acids are another vital class of organic compounds, characterized by the presence of a carboxyl group, COOH. This group consists of a carbonyl and a hydroxyl group attached to the same carbon atom. Carboxylic acids are found widely in nature, from the citric acid in fruits to the fatty acids in our bodies. Their acidic properties and reactivity make them essential in both biological and industrial processes. Carboxyl group is the defining feature of carboxylic acids. It combines a carbonyl group, C=O, and a hydroxyl group, OH, on the same carbon atom. This structure allows carboxylic acids to form strong hydrogen bonds both with themselves and with water molecules. The ability to donate a proton H+ makes them acidic, and this property is central to their behavior in chemical reaction. Carboxylic acids typically have higher boiling points than aldehydes and ketones due to their ability to form strong hydrogen bonds. Many lower carboxylic acids are soluble in water, but as the carbon chain length increases, solubility decreases. They often have sharp, unpleasant odors, especially in the case of short-chain acids like acetic acid. These physical properties influence their uses and handling in various industries. Carboxylic acids are known for their acidity, which comes from the ability to donate a proton from the COOH group. They react with bases to form salts and with alcohols to form esters in a process called esterification. Carboxylic acids can also be reduced to primary alcohols or converted to acid derivatives like amides and anhydrides. Their versatile reactivity makes them key players in organic synthesis. Unfamiliar carboxylic acids include acetic acid, found in vinegar, and citric acid, abundant in citrus fruits. Formic acid is present in ant stings, while lactic acid is produced in muscles during intense exercise. Fatty acids, which are long-chain carboxylic acids, are essential components of fats and oils. These examples show how carboxylic acids are woven into the fabric of life and industry. Functional group of an aldehyde, known as the formyl group, is central to its reactivity. This group is highly polar, making the carbonyl carbon susceptible to attack by nucleophiles. The presence of a hydrogen atom attached to the carbonyl carbon is what differentiates aldehydes from ketones and influences their chemical behavior. Ketone functional group is called the carbonyl group, where the carbonyl carbon is bonded to two other carbons. This arrangement makes ketones less reactive than aldehydes but still capable of undergoing important chemical reactions. The carbonyl group's polarity is responsible for many of the physical and chemical properties of ketones. Carboxyl group is a combination of a carbonyl and a hydroxyl group on the same carbon atom. This unique structure gives carboxylic acids their acidic properties and allows them to participate in a wide range of chemical reactions. The ability to donate a proton makes carboxylic acids important in both biological and chemical systems. Aldehydes are named by replacing the E ending of the parent alkane with al. For example, methane becomes methanal and ethane becomes ethanal. If the aldehyde group is attached to a ring, the suffix carbaldehyde is used. Proper nomenclature is essential for clear communication in chemistry, ensuring that each compound is uniquely identified. Ketones are named by replacing the E ending of the parent alkane with 1. The position of the carbonyl group is indicated by a number if necessary. For example, propanon is the simplest ketone, while butane 2,1 indicates the carbonyl group is on the second carbon. Accurate naming helps chemists avoid confusion and ensures precise identification. Carboxylic acids are named by replacing the E ending of the parent alkane with oic acid. For example, methane becomes methanoic acid and ethane becomes ethanoic acid. When the carboxyl group is attached to a ring, the suffix carboxylic acid is used. Mastering nomenclature is a fundamental skill for anyone studying organic chemistry. Aldehydes can be prepared by the partial oxidation of primary alcohols using mild oxidizing agents like PCC, pyridinium chlorochromate. Careful control of reaction conditions is necessary to prevent further oxidation to carboxylic acids. This method is widely used in both laboratory and industrial settings to produce aldehydes efficiently. Ketones are commonly prepared by the oxidation of secondary alcohols. Strong oxidizing agents like potassium dichromate or potassium permanganate are used for this purpose. The reaction stops at the ketone stage as further oxidation is difficult. This method is a staple in organic synthesis, providing a straightforward route to ketones. Carboxylic acids can be prepared by the complete oxidation of primary alcohols or aldehydes. Strong oxidizing agents like potassium permanganate or chromic acid are used to achieve this transformation. This method is widely used in both laboratory and industrial processes to produce a variety of carboxylic acids. Oxidation is a key reaction for aldehydes and carboxylic acids. Aldehydes are easily oxidized to carboxylic acids using oxidizing agents like potassium permanganate or Tollens reagent. Ketones, on the other hand, are resistant to oxidation under normal conditions. Understanding these reactions is crucial for both laboratory work and industrial applications. Reduction reactions are important for converting carbonyl compounds to alcohols. Aldehydes can be reduced to primary alcohols, while ketones are reduced to secondary alcohols. Common reducing agents include sodium borohydride and lithium aluminium hydride. These reactions are widely used in organic synthesis to modify functional groups. Both aldehydes and ketones undergo nucleophilic addition reactions due to the electrophilic nature of the carbonyl carbon. Common examples include the addition of hydrogen cyanide, alcohols, or ammonia derivatives. These reactions are fundamental in building more complex molecules in organic synthesis. Carboxylic acids react with alcohols in the presence of an acid catalyst to form esters, in a process called esterification. Esters are known for their pleasant fragrances and are widely used in the food and fragrance industries. This reaction is a classic example of how carboxylic acids can be transformed into valuable products. Aldehydes can be distinguished from ketones using specific chemical tests. The Tollens test uses a silver nitrate solution, which forms a silver mirror with aldehydes but not with ketones. The Fehling's test is another method where aldehydes reduce blue copper Roman II ions to red copper I oxide. These tests are valuable tools for identifying functional groups in unknown compounds. Ketones do not react with Tollens or Fehling's reagents, which helps distinguish them from aldehydes. However, both aldehydes and ketones react with 2,4-dinitrophenylhydrazine DNPH to form yellow or orange precipitates. This test is commonly used to detect the presence of carbonyl groups in organic compounds. Carboxylic acids can be identified by their reaction with sodium bicarbonate, which produces carbon dioxide gas. This effervescence is a clear indication of the acidic nature of the compound. Carboxylic acids also turn blue litmus paper red, confirming their acidity. These simple tests are widely used in laboratories to identify carboxylic acids. Aldehydes have a wide range of uses in industry and daily life. Formaldehyde is used in the production of resins, plastics, and disinfectants. Benzaldehyde is a key ingredient in flavorings and perfumes. The reactivity of aldehydes makes them valuable intermediates in the synthesis of pharmaceuticals and other chemicals. Ketones are widely used as solvents in industries such as paint, plastics, and pharmaceuticals. Acetone is a common solvent for cleaning and degreasing. Ketones are also used in the synthesis of various chemicals and as intermediates in the production of medicines and polymers. Their stability and solubility make them indispensable in many applications. Carboxylic acids are essential in the food, pharmaceutical, and chemical industries. Acetic acid is used in vinegar and as a preservative. Citric acid is a common food additive and flavoring agent. Fatty acids are crucial in the production of soaps, detergents, and cosmetics. The versatility of carboxylic acids makes them important in many sectors. Aldehydes, ketones, and carboxylic acids are not just important industrially, they're vital in biological systems too. Aldehydes are intermediates in metabolic pathways, ketones are produced during fat metabolism, and carboxylic acids are building blocks of amino acids and fatty acids. Their roles in life processes highlight the connection between chemistry and biology. Production and use of aldehydes, ketones, and carboxylic acids can have environmental consequences. Some aldehydes, like formaldehyde, are toxic and require careful handling. Carboxylic acids can contribute to acid rain if released into the atmosphere. Understanding the environmental impact of these compounds is essential for safe and sustainable chemical practices. In working with aldehydes, ketones, and carboxylic acids, safety is paramount. Many of these compounds are volatile, flammable, or toxic. Proper ventilation, use of gloves and goggles, and adherence to safety protocols are essential in both laboratory and industrial settings. Always consult safety data sheets before handling these chemicals. To wrap up, let's summarize the key differences between aldehydes, ketones, and carboxylic acids. Aldehydes have a carbonyl group bonded to hydrogen, ketones have it bonded to two carbons, and carboxylic acids feature a carboxyl group. These structural differences lead to distinct physical and chemical properties, influencing their uses and reactivity. You might be surprised to learn how often you encounter these compounds in daily life. From the vinegar in your kitchen to the acetone in nail polish remover, aldehydes, ketones, and carboxylic acids are everywhere. Their unique properties make them indispensable in food, cleaning, and personal care products. Research into aldehydes, ketones, and carboxylic acids continues to advance. Scientists are developing greener synthesis methods, new applications in medicine, and innovative materials based on these compounds. The future holds exciting possibilities as we learn more about their chemistry and potential uses. Let's test your understanding with a few review questions. What is the main difference between an aldehyde and a ketone? How can you distinguish a carboxylic acid from an aldehyde using chemical tests? Reviewing these concepts helps reinforce your knowledge and prepares you for further study in organic chemistry. Aldehydes, ketones, and carboxylic acids are foundational to organic chemistry. Their structures, properties, and reactions form the basis for understanding more complex molecules. Whether in the lab, industry, or nature, these compounds play essential roles. Keep exploring and applying these concepts as you continue your chemistry journey. Thank you for joining us on this exploration of aldehydes, ketones, and carboxylic acids. We've covered their structures, properties, reactions, and applications, highlighting their importance in both science and everyday life. Continue to build on this foundation as you delve deeper into the world of organic chemistry. Stay curious and keep learning.